All right, so let's start. So welcome to the fourth lecture of the physical biology module. Let's start by having a quick look at what we did in the last lecture. So in the last lecture, we were talking about thermal energy, thermal forces, and thermal motion. And what we saw that any object, any microscopic object can acquire certain amount of energy from the surrounding due to its interaction with the surrounding molecules, and that energy is given as kBT at any temperature T, and that is called thermal energy. And magnitude of this thermal energy at room temperature, which is generally taken as 300 Kelvin, is 4.141 into 10 to the power minus 21 joule. So the amount of energy that any object can acquire from surrounding is very, very small, and therefore this thermal energy doesn't matter much at the microscopic scale. But the moment you start to go to the microscopic scale, what happens that this thermal energy becomes very, very important. And there are two things that happen when you go to the length scale of biological molecules. What we saw that the different forms of energies become roughly of the same magnitude, and that's why biological molecules can very comfortably convert one type of energy into the other type of energy. And the other thing which we saw that the magnitude of different types of deterministic energies also become comparable to the thermal energy, and therefore a biological molecule or a microscopic system can simply acquire thermal energy from surrounding and can go from one state to the other state. And that led to a problem that if I'm doing an experiment with the system, in which state I will find the system. And prescription for that was given by Boltzmann. So what Boltzmann said that the probability of finding the system in any given energy state does not only depend on the energy of that particular state, but also on the fact how much thermal energy it can acquire from surrounding. And then we discussed the Boltzmann law, and we looked at its two applications. One of the application was to calculate the approximate height of the atmosphere, and the other application was to calculate the Nuss potential, which is the potential which is generated by the cell by having a concentration gradient of ions across the cell membrane. Okay. All right. So what we are going to do in this particular lecture, we are going to talk about another very important phenomena, which is called diffusion. Okay. And many of you have heard of diffusion in past. Okay. And whenever we talk about the diffusion, we generally say that diffusion is the process in which things move from the region of higher concentration to the region of lower concentration. Okay. Is it a correct statement? Anyone? Is it a correct statement that when diffusion is happening, things move unidirectionally from the region of higher concentration to the region of lower concentration? Anyone?
No, it is not unidirectional, but
okay. So what is happening here? Anyone?
like the molecules move in both the directions, but the rate of transfer in one direction is higher than the other.
Okay, yeah. This is somewhat correct. So when diffusion is happening, what is happening? Each of these diffusing molecule or particle is being bombarded by the thermal energy, and due to thermal energy, they perform a random motion. Okay, and that these molecules can go in any direction. Okay, similarly, these molecules will be also performing a random motion due to the thermal energy. But the fact is that there are more number of molecules in this region than in this region. So molecules are also going in this direction as well as in this direction. Similarly, molecules which are here, they are going in this direction as well as in this direction. But the fact that there are more number of molecules which are going from left to right than from right to left, we have a net flux which is directed in the direction of the region of lower concentration. Okay, so things on average move from the region of higher concentration to the lower concentration. So there is a net flux which is directed towards the direction of lower concentration. All right. So many of you have also seen the process of diffusion in the real life, right? For example, if you take a beaker of water, you put a drop of ink, right? Initially, drop of the ink is confined to a small region, but gradually what will happen that the drop of, these ink molecules will start to diffuse, and then the entire color of the beaker will have the color of the ink, right? Similarly, let's say if I have a bottle of fragrance, I open it, what will happen? Initially, when I'm opening it, I will get the smell of it. Okay. Then after some time, person who is standing, let's say 1 meter away from me, will get a smell of it. Then after some time, person who is standing at a distance of 5 meters will get a smell of it, right? And so on. So what is happening in this process? That initially the substance was near the bottle or inside the bottle, but after some time it will be found at a distance away from the bottle. So there is a change in concentration with respect to the time. Okay. So at t is equal to 0, everything is near the bottle or inside the bottle. And then for time t greater than 0, it will be at a location where it was not earlier. So there is a change of concentration with respect to time. And then there is also a change of concentration with respect to space, because initially all the molecules, fragrance molecules, were in the bottle, and then after some time they are at a distance where they were not there. So when diffusion is happening, what is happening? That there is a change of concentration of these diffusing molecules with respect to space as well as with respect to time. Okay. So what we are going to do now is we are going to derive an equation which is known as diffusion equation. And what it does, it links the change of concentration in time to change of concentration in space. Okay. And diffusion equation is an equation which can be obtained by combining two laws. One of them is called Fick's law, the other one is called continuity equation. And sometimes in some textbooks it is also written as Fick's first law and Fick's second law. Okay, so let me switch to my iPad and let's try to derive the diffusion equation. But what I will do, for sake of simplicity, I will not derive the diffusion equation using rigorous mathematics. What I will do, I will try to derive it by giving you some qualitative arguments. Okay. All right. So let me stop sharing this screen. And then let me go to the screen. All right. So what I'm saying, that when, let's say we have a diffusing substance, let's say a fragrance molecule. Okay. At t is equal to 0, everything is here. Okay. And then for t greater than 0, due to diffusion, molecules will be here. Okay. So what is happening here, that there is change of concentration with respect to space as well as with respect to time. And what we are going to derive is called diffusion equation. And what it does, it connects the change of concentration with respect to time to change of concentration with respect to space. Okay. And as I said, that this diffusion equation can be obtained by combining two laws. One of them is called Fick's law, and the second one is continuity equation. So let's try to see what is Fick's law and what is continuity equation. Okay. So let me draw here three different types of concentration profile. Concentration profile means how the concentration is changing with respect to space. Okay. So one of them is a flat concentration profile. The second one is, let's say, something like this, where there is more concentration on one side, on the right hand side, on the left hand side, to the right hand side. Then the third one is here, which is less concentration on the left hand side and more concentration on the right hand side. Okay. Now, question for all of you: what is the value of delta C by delta X in this case? Anyone?
0.
0. So when we have a flat concentration profile, will there be a net transport of a net movement of molecules from one side to the other side, or will there be any diffusion? Yes or no? If we have a flat concentration profile, will there be any net movement of the molecules from one location to the other?
No.
Yourself? No, right? So in this case, I can say that the net flux or net current of particles, okay, will be equal to 0, right? What is the value of delta C by delta X in this case? Positive or negative?
Negative.
Negative. Now, if we have this kind of concentration profile, what will be the net direction of movement of particles? Or what will be the value of J? Will it be negative or positive? Anyone? What will be the net direction of J in this case?
Positive.
Okay. In this case, we can see that the flux will be directed in this direction, and therefore J will be positive. The value of delta C by delta X in this case is positive. What will be the net direction of the flux in this case? It will be in this direction, and the value of J will be negative. Okay. Now, from these three different concentration profile, please mute everyone. Please, there is some noise which is happening. Yes, somebody raised the hand. Om, you have a question? Om, do you have a question? Please unmute yourself.
Sir, I don't have a question.
Okay, fine. All right. So what we are doing here, that we are going to make two different inferences from these concentration profile. What you can see that in order to have a finite J or a non-zero J, we require a non-zero delta C by delta X. That means J depends on the value of delta C by delta X. If delta C by delta X is 0, then J is 0. The J will be non-zero only when we have a finite delta C by delta X. Somebody's microphone is making a lot of noise. TS, please identify and remove that person from the meeting if possible. All right. So first thing we learn that in order to have a finite J, we require a finite delta C by delta X. And the other thing we see is that if delta C by delta X is negative, then J is positive. And if delta C by delta X is positive, then J is negative. That means J depends on the value of the delta C and the delta C by delta X, but in a opposite manner. Okay. So that means J is proportional to minus delta C by delta X. So that if delta C by delta X is negative, then J becomes positive and vice versa. Right? Now, whenever we have a symbol of proportionality, we replace it with a constant. And we put this constant as D. Now, here in this case, D is called the diffusion constant or diffusion coefficient. All right. Now, this is what is called Fick's law. Okay. So, without any reverse mathematics, I gave you the expression for the Fick's law. Now, we have to derive the diffusion equation, and for that, we have to combine the Fick's law with the continuity equation. Now, let's see what is continuity equation. Suppose my IIT Bombay is situated on a straight road, which it is on JBLR, let's say. Okay, and this is my IIT Bombay campus. Okay, let's say this location is X. This is X plus delta X. Okay, two boundaries. Okay, Now, suppose I'm counting how many cars are coming to IIT Bombay in an hour, per unit hour. Okay. And if more number of cars are coming to IIT Bombay per unit time or per hour, then I will denote them with a large number of arrows. Okay. So let's say on a particular day, I am counting how many cars are coming to IIT Bombay campus per unit time. Okay. So let's say certain number of cars are coming to IIT Bombay on a given day. Okay. So I'm denoting if the flux of vehicles by the number of lines. If there are more number of lines, then there is a higher flux. Okay. So let's say that on a given day, certain number of vehicles or cars are coming to IIT Bombay, which I will denote by C, and a large number of vehicles are getting out of the campus in the same amount of time. Okay. So let's say the J is low, incoming J is low, but outgoing J is high. Okay. Right. Now X is having a lower value here, X is having a higher value here. Okay, X is delta X. So in this case, what you see that the value of delta J by delta X will be greater than 0. If less number of cars are coming to IIT Bombay campus per unit time and more number of cars are getting out of IIT Bombay campus per unit time. Now, if I look at the number of cars which will be inside IIT Bombay campus per unit time, those number of cars per unit time will increase or decrease under this scenario. That means what will be the value of delta C by delta T? Will it decrease or increase under this scenario? Anyone? Anyone? Please unmute yourself or raise your hand.
So can you repeat the question?
I'm saying that if less number of cars are coming to IIT Bombay campus per unit time and more number of cars are getting out of IIT Bombay campus per unit time, what will happen to the number of cars per unit time in IIT Bombay? Will it decrease or increase? Anyone?
Decrease.
It will decrease. That means delta C by delta T will have a negative value. All right. When delta J by delta X is having a positive value. Now let's talk about an alternative situation. Suppose more number of vehicles are coming to IIT Bombay per unit time. Okay. So that is, let's say J is high, and less number of vehicles are getting out of IIT Bombay campus per unit time. In the second case, what will happen? That delta J by delta X will be less than 0 because J is low on this side, J is high on this side. And in this case, if more number of vehicles to coming to IIT Bombay per unit time and less number of vehicles are getting out of the campus per unit time, then the number of vehicles or cars per unit time will increase, right? That means delta C by delta T will be greater than 0. Now I will take the example of my household. Suppose I am earning, let's say C denotes the number of currency notes in my house. Okay. So let's say I'm bringing a large number of currency notes to my house per month, and my family members are spending less number of currency notes per month, then number of currency notes in my house will increase until I start to borrow additional money from somebody or I start to lend money to someone else. Okay. So this is what is called continuity equation, and this is based on the conservation of integer. Now from this argument we can see that delta C by delta T is in fact related to delta J by delta X by this relation. Okay. So this is what is called continuity equation, right? Is this clear? If I'm bringing more amount of money to my house per unit month and my family members are spending less, then the currency notes in my house have to increase. per month. Okay, so this is strictly based on the conservation of the material, and that tells me that delta C by delta T has to be related to delta J by delta X in this manner. Okay, now what we have to derive is diffusion equation. Okay, and I say that diffusion equation is something which you can obtain by combining Fick's law and continuity equation. Right? So what I will do? We already know the Fick's law, right? Fick's law is what? J is equal to minus D delta C by delta X, right? What I will do? I will put the Fick's law into this equation, or the value of J. What I will get is delta C by delta T is equal to D delta 2C by delta X. What we get is a simple differential equation, and this equation is called diffusion equation. But you see that what it is relating? It is relating the change of concentration delta C by delta T with respect to time, change of concentration with respect to time, to change of concentration with respect to space, which is delta C by delta X. Right? Now, what I would like to ask from you, have you seen any similar equation before? Anyone? Have you seen any similar equation before? Any student, please unmute yourself.
The heat equation.
Which heat equation looks like this? Yes, very nice. Anything else?
The Schrodinger equation.
Schrodinger equation also looks like this, very nice. And wave equation also looks like this, right? So heat equation, wave equation, Schrodinger equation, all of these equations look like this. And all of you also know that it is not very easy to solve either Schrodinger equation or heat equation or wave equation for complex systems. Okay, the solution of these equations can be obtained for a very simple situations. So what we will do again in this lecture, we will not try to solve the diffusion equation. What we will do, we will look at the solution of diffusion equation for a very simple case, which is of our interest. Okay, Mr. Sahu, you raised your hand. Any question?
No, sir, it was by mistake.
Okay, all right. So what we are going to do, we are not going to solve the diffusion equation because it's very difficult to solve diffusion equation for complex systems. We will look at the solution of the diffusion equation in a very particular case, which is called diffusion from a point source. Okay, what is the meaning of diffusion of a point source? That something is really very much concentrated at one place. So suppose this is my X and I have very high concentration of something at one place. Okay, if I have to mathematically represent very high concentration or very high function value at a given point, how do we represent it mathematically?
Delta function.
Delta function, very good. So suppose the concentration is picked like a delta function. Okay, right? Okay, and we are going to look at how the solution of the diffusion equation will look like in this case, right? So initially at t is equal to 0, let's say the function is like a delta function. Okay, if you have to compare it with a similar situation, suppose you have very high concentration of fragrance in a very in a tiny bottle. Okay, and then at t is equal to 0, you remove the cap. Okay, so initially everything was concentrated like a delta function at the bottle, but for if you look at the concentration of the particle after just right after the opening, you will see that concentration at the origin will decrease, and you will also find the fragrance molecules in the surrounding. Okay, let's say this is time t. Then if you wait for some more time, the concentration at the origin will further go down, and it will again spread to larger distance. If you again wait, for some more time, it will again further go down at the origin and it will even spread more. And if you wait for long enough time, the substance will be found everywhere in the space, right? So qualitatively, this is how you expect the solution of this function to look like. And in fact, if you solve the diffusion equation with this initial boundary condition, then what you are going to get is basically by solving the diffusion equation, you are going to get the value of Cxt. Okay, and if you solve it, what you are going to get is that the solution of the diffusion equation will look like this. Okay. And this will be just like a Gaussian function. Okay, so let me, right, what is happening here, the particles are going in both directions, right, because of the diffusion. The same similar equation can be also written for a probability density, right? Now suppose a particle is diffusing like this, okay, where it can go from 0 to plus infinity or minus infinity with equal probability, right? And then if you try to calculate the average displacement of such diffusing particles, what will be the average displacement? If they can go to the positive direction as well as to the negative direction with equal probability,
0.
right? So whenever we have a variable which can go into the positive as well as in the negative direction, we never calculate the simple average, right? Generally what we calculate, mean square displacement or root mean square displacement. Okay, the whole idea is that you first square the the values of the quantity so that even the negative ones become positive, and then you take the mean. Okay, so since this is the same situation here, we don't calculate the simple average because we know that simple average is going to be equal to 0. What we have to calculate here in this case is x square, mean square displacement. And if we calculate the mean square displacement for this kind of system, mean square displacement will come out to be 2dt. Okay, let's say if this is the equation in the probability density, you can verify it. Okay, all right. Now, so this is what you are going to get for the case of one-dimensional diffusion, when things are diffusing only along x direction. But let's say if the diffusion is happening in 2 dimension, then you will have x square plus y square, and as a result r square will become 4 dt. Similarly, if the diffusion is happening in all the 3 directions, then the value of mean of the square of displacement will become 6 dt. This is for 3D diffusion. This is for 2-dimensional diffusion. All right. Now,
Sir,
yes.
sir, why would it be simple addition like in X, Y, and Z? Like, why won't
I mean, you can verify it yourself because this is something which I also sometimes give it as a numerical problem, because it will be a simple sum of average of x square plus average of y square. Okay, and this way it will come out to be as r square is equal to 4dt. You can check it yourself.
Yes, sir. Got it.
Okay. All right. And if you have to check whether this is indeed true, what you have to do, you just simply okay, if you have to see whether this is indeed a solution of the diffusion equation, how will you check that? You will simply put this thing into the diffusion equation. You will see that right hand side will be equal to the left hand side, right? This is how you can verify that this is indeed the solution of the diffusion equation. All right. Now, what we see here is a very interesting thing. Okay, that when the diffusion is happening, then if you look at the square of the displacement of the particle, it is proportional to t in case of diffusion. X square is proportional to t. So there are two ways in which a particle can go from one place to the other place. Okay, One of them is called ballistic motion, in which particle goes from one place to the other place with certain velocity, let's say v. And if you have that kind of situation, if you plot x versus t, in this case, what do you see? That it will be a straight line. X will be proportional to t in case of a ballistic motion. Okay, if something is going unidirectionally from one location to the other location. However, if something is going from one place to the other place by doing this back and forth, back and forth, back and forth, back and forth movement, that is a diffusive motion. And when something is going from one place to the other place by performing this back and forth, back and forth, back and forth motion, then in that case, it is not the x which is proportional to t, but it is actually x square which becomes proportional to t, or x becomes proportional to t to the power half. Okay, so in case of a ballistic motion, we have this kind of dependence with respect to time. But if something is diffusing, then in that case, if you look at x versus t looks something like this. Okay, so here x is proportional to t to the power half in case of diffusion motion. What you see from this diagram is very interesting, that for shorter time scales, diffusion can be a efficient process, but on longer time scales, when the t value is very large, the average displacement of the particle is much more smaller than something which is moving ballistically. Okay, so this is why we say that diffusion is a very slow process. Sometimes we perceive that we open the bottle of fragrance, we immediately get the smell. Okay, and we get an impression that diffusion is very fast. No, actually diffusion is a very slow process. Okay, on longer time scales. Okay, and how slow it can be, let me illustrate that by using a slide. Okay, so let me share my slides first. Okay. See, we know that our cells require supply of ions, protein, as well as organelles from one place to the other place for survival. Okay. Now, suppose I have an ion. We know all the physical properties of the ion, and if you calculate how much time an ion will require to diffuse over a distance of 1 micron, which is typically the size of a small cell. Okay, it will take 0.25 milliseconds. To diffuse over a distance of 100 microns, it will take 2.5 seconds. To diffuse over a distance of 10 millimeters, it will take 7 hours. But if an ion has to diffuse over a length scale of 1 meter, it will take 8 years. Okay. Oh, I'm sorry. You are not seeing the screen, right? Just one second. I'm sorry. Just one second. Thank you. Is it visible now?
Yes, sir.
Our body requires supply of ions, protein, and organelles for survival. Okay, and we know the properties of average size of the proteins, organelles, okay, and ions. Now, suppose if I have an ion, and if it has to diffuse over a distance of 1 micron, if it has to travel a distance of 1 micron by the process of diffusion, then this ion will take 0.25 milliseconds. For 100 microns, it will take a distance, it will take a time of 2.5 seconds. If it has to diffuse over a distance of 10 millimeters, then it will take 7 hours. And if an ion has to diffuse over a distance of 1 meter, then it will take 8 years. Now, I know that some of my cells are about a meter long. They go from my head to toe, right? Some of the nerve cells. And if an ion has to go from my head to toe by the process of diffusion, it will take 8 years. Okay, obviously my cells cannot wait for 8 years to get the supply of ions that way, right? Now, protein, let's say if I take my favorite protein, 100 kilodalton protein of 3 nanometer size. Okay, if I calculate how much time it will take to diffuse over a distance of 1 micron, 5 millisecond, 100 micron, 50 seconds. For 10 millimeters, it will take 6 days. But if it has to diffuse over a distance of 1 meter inside my body, it will take 150 years. And I know that my lifetime is on average is not going to be more than 100 years. Okay. So my cells cannot wait for 150 years to get the supply of protein by the process of diffusion. Similarly, if you look at the organelles, let's say mitochondria, whenever you get an injury somewhere in the body, a lot of mitochondria which are inside the cell have to be rushed to that location at the site of the injury, because that part of the cell requires a lot of energy. Okay. And if let's say mitochondria has to reach over a distance of 1 micron by the process of diffusion, it will take 1 second. For 100 micron, 3 hours. For 10 millimeters, 3 years. But if it has to diffuse over a distance of 1 meter, then it will take 30 millennia. That means 30,000 years. So obviously our cells cannot utilize the mechanism of diffusion to survive. Okay. And the other thing is that diffusion is a very, very slow process. It takes a lot of time for diffusion to happen. In order for diffusion to happen, you also require very, very high concentration of something in one place, which is sometimes not possible for cells to create. And the other problem with the diffusion is that diffusion is isotropic in nature. That means when diffusion starts to happen, things spread in all directions with uniform probability. I want to send the things inside the cell from point A to point B, but when diffusion will start to happen, it will go in every possible direction. Okay. So obviously our cells cannot utilize this mechanism of diffusion for transporting things inside the cells. What our cells do, they use very specialized proteins, which are called motor proteins, to transport things from one place to another. Okay. So what I'm going to do now, I'm going to play a movie which shows the different type of motor proteins which our cells use for transporting things inside the cells. And I would like to also tell you that this is an animation which is based on most of the scientific facts which are known about the motor proteins, because I also work in a similar area. Okay. So whatever you see in the animation is actually based on most of the scientific facts which are known about the motor proteins. So let's watch this movie and then I will talk about it. All right.
Our brain is made of billions of nerve cells, and they're all connected. If we take a closer look, a nerve cell seems to have antennas. Most of them are receivers of information, but only one is a transmitter, called the axon. This axon is connected to several receivers of other cells, forming a gigantic neural network, the brain. Meet John. John is a kinesin, a motor protein. He lives inside a nerve cell and he has a proper job. To ensure that a brain cell does his job properly, it needs the continuous flow of building materials, proteins. They travel through the cell using the cytoskeleton. If you would compare a nerve cell with a city, the cytoskeleton inside the cell would be the roads, and the traveling proteins would be the traffic. These materials are towed by motors along the roads. And just as in real life, there are different kinds of motors and different kinds of roads. John's sole purpose in life is to deliver his cargo to a specific place in the axon. He takes the main roads, and he walks in just one direction only. John's job may seem easy, but it's not. He has to overcome a number of obstacles to ensure that the right amount of cargo arrives at the right place. To make the journey even more difficult, John is not alone. Other motor proteins ride along with his cargo. They haven't woken up yet, but that will happen soon. The journey starts in the center of the city, just like in the center of the cell. To enter the axon, John has to pass a place called the axon initial segment. In this segment, there are two kinds of roads. The main roads that John uses, called the microtubules, and a lot of little alleys called actin. And here, our brave motor protein meets his first challenge, because one of his sleeping travel companions, myosin, has woken up and starts to cling to the actin. And there are a lot of alleys. Only brute force can save John now. Fate strikes again. The other companion, Dynin, wakes up, and he can only walk in the opposite direction of John, resulting in a tug of war. But there can be only one. Along the axon in which John travels, there are places called synapses. Here, the axon connects to receivers of the other cells. Regulating proteins call the shots here. This traffic police makes sure that all passing traffic gets to the right destination. If John's cargo is needed in this synapse, he will be stopped and myosins take over his load. But today, John's cargo is safe. But what he does not know, that his road is under construction just a few blocks away. In our nerve cells, the cytoskeleton is changing constantly. Roads are built, but are also broken down. Facing this kind of obstruction, John has to find a detour. John isn't the only motor protein on the road. There are many more. Our nerve cells need a smooth traffic flow in order to perform well. A traffic jam due to problems during the journey may ultimately result in brain disease. Understanding the challenges John faces could improve treatment or prevention. Finally, John arrives at his destination. He has fulfilled his destiny. But several other Johns are just getting started.
All right, so we'll stop this here. So if you look at the typical structure of a cell, okay, this is how the typical structure of the cell looks like. Okay, you can think of that cell is like a city, and these structures which are shown in brown are like microtubules. Okay, so they originate from the cell center and they go all the way up to the periphery. So they are like long range highways in the city. And then along the cell periphery, we mostly have short filaments, which are actin filaments, which are like local roads. So anything which has to go from cell center to cell periphery has to take these highways and then has to switch to these local roads. Similarly, anything which has to go from cell periphery to the cell center has to first take local roads, then it has to switch to the highways. Okay. Now, along these highways or microtubules, we have two different type of motor proteins that move. One of them is called kinesin, the other one is called dynein. So kinesin mostly moves from cell center to the cell periphery, whereas the dynein motors move from cell periphery to the cell center. Similarly, along these short roads or actin filaments, we have different type of myosin motors that move along these actin filaments, and these are called unconventional myosin motor. Our myosin motors which are found inside the muscles. When I move my muscle, there are myosin motors which slide on the actin filament. They are called conventional myosin because they stay in one place and generate the force required for muscle movement. But these myosin motors can physically move from one place to the other place inside the cells. That is why they are called unconventional. All right. Now, if you look at any one of the physiological cargoes, what you find that these physiological cargoes can have different types of motors on them. For example, if you look at this cargo which is moving along the microtubule, it can have kinesin as well as dynein motors, and they move in opposite directions. Now, being an engineer, you will say that why nature has designed this kind of an efficient system, because if you look at it, okay, then what you see that there are two different types of motors, and therefore they will try to move in opposite direction. And I know that movement of these motor proteins require energy, because these motor proteins hydrolyze ATP to generate the forces. So you feel that, okay, they are just wasting their energy, okay, in trying to fight with one another. And when something has to be transported from one place to the other place, then you will try to put the people who actually move collectively in a direction. But what you see here, that there are both types of motor proteins which have been put on the cargo, and therefore they will waste a lot of time in, and they will engage a lot of times in a tug of war. They will keep fighting all the time. So this will be wastage of time, and this will be wastage of energy. Okay, but it turns out that nature has designed this kind of system during the process of evolution with a lot of thought. Just to give you an example, few examples, like, if you have got different type of motors, then by sending some signal or having the regulatory molecules, you can tune the number of motors on each side, and you can control the velocity and the distance to which these cargos can travel. If you have got both types of motors, and let's say if the cargo has encountered an obstacle, then it cannot go back. Okay, but if you have got the other kind of motors, it can engage other kind of motor, it can walk back, and then it can take the correct direction. Okay, so this kind of mechanism has got its own advantages, and nature has designed it with a lot of thought. Okay, so this was all about the diffusion, why diffusion is a very slow process, and why our cells cannot utilize the mechanism of diffusion, and why our cells need motor proteins to transport things from one place to the other place, and how this transportation is done with the help of motor proteins. Any questions? All right, so if there is no question, then what we would like to do now, after discussing diffusion and active transport by motor proteins, we would like to talk about Einstein and Einstein relation. Okay, so I don't know how many of you know that there is also a relation in Einstein name that is called Einstein relation. Okay, and it is not E is equal to mc square. So this is a BB101 lecture, and I am talking about Einstein in this lecture. Any idea why? Any thoughts? I talked about diffusion, and then now I'm jumping to Einstein and Einstein relation. Is there any connection? Anyone? All right. Okay. So let me tell you that if you look at the history of the science, then year 1905 is called the golden year of physics, because in this year Einstein wrote 3 papers. His first paper was on photoelectric effect, the second one was on something called Brownian motion, and the third one was on special relativity, and fourth paper was an extension of the third paper, where he derived the relation E is equal to mc square. Okay, and we also know that Einstein got Nobel Prize. Okay, and whenever I talk about Nobel Prize, I say that Nobel Prize is not given for doing the trivial discoveries. Okay, so I hope all of you know that Einstein got Nobel Prize for which one, which work? Anyone?
Photoelectric effect.
For photoelectric effect. Why he got the, and I say I made a statement that Nobel Prize is not given for doing the trivial scientific work. What was the non-trivial thing he did? Any thoughts on that?
It proved the particle nature of light.
So what? What was the novelty of the work? I mean, why proving the particle nature of light mattered at that time?
Because there was a debate over the corpuscular theory and the wave theory. So
Which theory?
corpuscular theory, like the particle nature of light.
Any other thought? Anyone else? why his work on, so he got Nobel Prize for photoelectric effect. He got the Nobel Prize for doing the experiment or explaining the phenomena? Anyone?
For explaining.
Explaining. And why explaining photoelectric effect was important?
I mean, Planck he wasn't able to explain that. I mean, he did the experiment before Einstein, right?
Go ahead. I'm listening. Yeah.
Yeah, but I mean, Einstein was properly able to explain that, and there was a research paper, I guess, in 1901 that Einstein published.
But my question is why it was important to explain that?
Um,
Okay, so let me quickly give you the answer. So during the time of Einstein, right, there was one mechanics which we know as classical mechanics. Classical mechanics could virtually explain everything starting from motion of small objects like pendulum to the motion of planets. Okay, but classical mechanics could not explain few observations like black body radiation and photoelectric effect. Okay, and people needed a different kind of mechanics. Okay, so his explanation of photoelectric effect gave rise to a new area of physics that we know as quantum mechanics or quantum physics today. Okay, and that is what he got the, that is why he got the Nobel Prize. Okay, so we know that this was an important work. Many of you also understand that he made a great contribution to the theory of special relativity, and we understand the importance of E is equal to mc square. You know, it was heavily used during the World War, and you know, many people think that he should have also got the Nobel Prize for that, and many people do not actually even know about his work on Brownian motion and what was his importance. It turns out that his work on Brownian motion was also equally important at that time. Okay, and that is what I'm going to discuss now. Okay, so what I'm going to first do, I'm going to derive the Einstein relation, but I will not take the approach which Einstein had taken because it is slightly complex to be discussed in this class. What I will do, I will take a much simpler approach to derive the Einstein relation, and then we'll try to understand what was the importance of the work which he did. Okay, all right. So for that, what I will do, I will take the example of a colloidal solution. Okay, now what is the property of a colloidal solution? Anyone? What do you know about a colloidal solution?
It has particles in the range 1 to 1000 nanometers.
Okay, any other property? What is the property of colloidal suspension? Okay, and milk is one of the best example of colloidal suspension or solution, right? Why? What is the property of colloidal suspension? So colloidal suspension has a property that if you take a colloidal solution or suspension in a container, these colloidal particles will never sediment. They will never go to the bottom of the container. Okay, they will always remain suspended into the liquid, right? So that is the unique property that a colloidal suspension has. Okay, so what I will do, I will take the example of colloidal suspension. Okay, now here what is happening that, you know, since there is no sedimentation, even if particles are moving, the particles have to move in such a way that whatever number of particles are going downward, the same amount of particles have to also go upward. Only then this solution will not sediment. There will not be accumulation of particles anywhere, either at the top or at the bottom, right? So in order to derive the Einstein relation, I'm taking the example of colloidal suspension. Okay, so suppose here I have a particle and there is some force F acting on this particle. Okay, let's say the height of the solution is X. Okay, so let's say the concentration here is C0 and concentration here is, let's say, something like Cx. Okay. Now, if there is some force acting on each of these particles, let's say this force is F. I'm not worried about the nature of the force. I'm just saying that there is, let's say, some force acting on these particles. Now, if some force F is acting on this particle, we can write down the expression for the current that will be there due to this force acting on the particle. Now, this force, which can be gravitational force or combination of many other forces, will try to drive the particles downward. And we know that this is a colloidal suspension. What will happen in this solution? That since particles are coming downward, there is also thermal energy, right? These particles are suspended in the fluid, and therefore they will be kicked by the thermal energy from all sides, and therefore whatever is coming down has to be compensated by the flux due to the diffusion, right? Only then the particles will either accumulate at the top or at the bottom if the flux remain balanced. So what I can do, I can write down the expression for the flux due to this force which is acting on these particles. Okay, and I can write down this thing as C into V. Okay, and this can be written as C F is the force acting on the particle divided by 6 pi eta R using the Stokes law or drag coefficient. Okay, so this becomes as minus C F divided by 6 pi eta R into, let's say, I. Similarly, we can write down the expression for the diffusion flux using the Fick's law, right? I can apply the Boltzmann law to this problem, and I can write down that Cx will be equal to C0 e to the power minus Fx divided by kBt. And if I use that, I can write this down as minus d delta C by delta x into I, and this will be equal to dCf divided by kBt into I. Now we know that since this is a colloidal solution, and therefore both the fluxes have to be balanced, and therefore Jf plus Jd, their vector sum has to be equal to 0. If I use that, what I get is that Cf divided by 6 pi eta R into I is equal to dCf divided by kBt into I, or what I get is 6 pi eta R d is equal to kBt. Now we know that 6 pi eta R is nothing but is the drag coefficient, and therefore I can write down this thing as gamma d is equal to kBt. So this relation is called the Einstein relation. Gamma d is equal to kBt is called the Einstein relation. So we have derived the Einstein relation, and now we have to see the importance of this relation. Yes, Kandar.
Sir, can you please explain like what was F in the previous slide?
F is some force which is acting on these particles. It can be gravitational force. I'm not concerned about the origin of what is the source of this force. I'm saying that let's assume that some force F is acting on these particles. Okay, so due to that, particles will try to move down. But we also know that if particles are moving down, then the entire flux, there has to be also an equal amount of flux in the opposite direction. Okay.
Okay, sir. Thank you, sir.
So this is the Einstein relation. Okay. Now, what is its importance? So first thing, what you can see that in thermal equilibrium, if there is a thermal equilibrium, that means the value of T will be constant and Kb is always constant, and therefore in thermal equilibrium gamma d is a constant quantity. Okay. So Einstein relation tells you that in thermal equilibrium, the product of gamma and d is a constant quantity, and therefore the gamma and d are related to one another by an inverse relation. Okay, so what it tells you that in thermal equilibrium, the drag and diffusion try to balance one another. If one of them increases, the other one has to decrease. Okay, so what Einstein relation tells you that in thermal equilibrium, the gamma and the drag coefficient. So gamma, the drag coefficient, and D, the diffusion constant, try to balance one another. Their product is a constant quantity, and therefore, if one of them decreases, the other one has to increase. Okay. Now here, so this is the measure of the drag acting on the particle, and this is the diffusion, right? So whenever diffusion is happening, the particle is moving back and forth, so there is some fluctuation. Okay, and whenever we have drag, recall my first lecture, whenever we have drag, it leads to dissipation in the system. Okay, so sometimes this is also called as one of the elementary forms of fluctuation dissipation relation. It connects fluctuation to the dissipation. Okay, right? But this was not the importance of the work that Einstein did in the year 1905. The importance of the relation was something else. Okay, so we know that the Einstein relation tells you that in thermal equilibrium, gamma D has to be a constant quantity, and gamma and D are inversely related to one another, so that if one increases, the other one has to decrease. Okay, the importance of this relation was something else. Okay, and that is what we are going to discuss now. So I'm talking about the year 1905. So this is year 1905. Do you think that in year 1905 people believe in the existence of atoms and molecules? How many of you think that people believed in the or scientists believe in the existence of atoms and molecules? Please raise your hand. I want to see. How many of you think that in year 1905 people believed in the existence of atoms and molecules? Please raise your hand. If you think that by year 1905 people had started to believe in the existence of atoms and molecules, please raise your hand. Keep raising quickly. I will give 1 minute. Please raise your hand if you think that in year 1905 it was established that atoms and molecules do exist. Few more seconds, I will wait. So about 30 students have said that in year 1905 scientists believe that atoms and molecules do exist. Okay, now if you go and check the history of the science, you'll be surprised to know that even in year 1905, okay, scientists did not believe in the existence of atoms and molecules. There was a lot of discussion whether atoms and molecules exist or not. Okay, so let me share my slides. Okay, so if you go back and check, what you'll find that the Thomson model came in 1904, the Rutherford model of atom came in 1911. So by year 1905, there was still a lot of discussion whether atoms and molecules exist or not. And at that time, there was a theory which is called molecular kinetic theory of heat, where people use the words particles rather than atoms and molecules. So, people thought that the heat content of a given object is coming because of the motion of the particles which are there in the substance. Okay, but nobody wanted to use the word atoms and molecules because the existence of atoms and molecules was debatable at that time. And what Einstein's relation did at that time, that one could use this Einstein relation in year 1905, and one could calculate the Avogadro's number with a lot of accuracy using just a simple microscope and a stopwatch. Okay, so we have derived the relation gamma d is equal to kBt, right? So what we can do, we can write down that, let me have the pointer, that d will be kBt divided by gamma, which is 6 pi eta r. We know that the product of the Avogadro's number and the Boltzmann constant is another constant, which is r, ideal gas constant. So we can rewrite this entire equation as RT divided by n 6 pi eta r. Okay. Now this is the relation which Einstein had derived in his original paper in 1905. So you see that r is here, t is here, n is here, 6 pi is here. So instead of using the symbol eta for the viscosity, he is using the symbol K. Instead of using symbol R for the size of the particle, he is using symbol P. Everything else is identical. Okay. Although I took a much simpler approach to derive it. Okay. And using this relation, one could use a simple stopwatch and a microscope to find out the Avogadro's number. Let me tell you how one could do this. Okay. Let me switch to my iPad. All right. So what we have to determine, so the relation is given as, this is RT divided by n 6 pi eta r, right? Now we have to determine this Avogadro's number. We know that r is a constant, 6 is a constant, pi is a constant. Okay. Now here, if I have to determine the value of the Avogadro's number, what I can do, I can take a particle of known size, let's say radius r. I can put the particle into a medium of known viscosity, so I can fix the value of eta. So eta I can fix the value of r, and I can also control the temperature of my experiment. I can do the entire experiment at a finite temperature, so I can also make this as a constant. Now, if I can measure the diffusion constant of this particle, then from the knowledge of that, I can determine the Avogadro's number. How do I measure the diffusion constant of this particle? What I do, I look at since this is a microscopic particle, this will have a zigzag motion, let's say in a 2D plane, and I can use the relation r square is equal to 4 dt, right? So in order to measure the r square of the displacement, I will require a microscope, and to measure the time, I will require a stopwatch. Okay. And I can determine the value of d. I put the value of d here, and I can calculate the values of Avogadro's number. So power of the Einstein relation was that even in year 1905, one could do a simple experiment with a microscope and a stopwatch to calculate the Avogadro's number. And if you can calculate the Avogadro's number, you are giving us very strong support to the notion that atoms and molecules do exist. Okay. Now, just 1 second. Let me share this screen.
Sir,
Yeah, just hold on. I will take the question. Okay. Okay. Einstein did all of this in year 1905, but Einstein was not very sure about what he did. Okay. So this is the English translation of his work, which was originally published in German. I have also uploaded this paper in the Moodle. So title of the paper was On the Movement of Small Particles Suspended in Stress Liquid Required by Molecular Kinetic Theory of Heat. And what Einstein says that it will be shown in this paper that according to molecular kinetic theory of heat, bodies of microscopically visible size suspended in liquid must, as a result of thermal molecular motion, perform motion of such magnitudes that these motions can be easily detected by a microscope. It is possible that the motion to be discussed here are identical with so-called Brownian molecular motion. He is not very sure. However, the data available to me on the latter is so imprecise that I could not form a definite opinion on this matter. If it is really possible to observe the motion to be discussed here along with the laws it is expected to obey, then classical thermodynamics can no longer be viewed as strictly valid even for microscopically distinguishable spaces, and an exact determination of real size of atoms becomes possible. Conversely, if the prediction of this motion were to be proved wrong, this fact would provide a weighty argument against the molecular kinetic conception of heat. So what Einstein said that, okay, I think what I have discussed here is the Brownian motion. One should be able to detect the motion of microscopic particles using a microscope. So Einstein did all of this, and using his Einstein relation, one could calculate the Avogadro's number at that time, which, and therefore, his theory of Brownian molecular motion also gave a very strong support to the molecular kinetic theory of heat, okay, which was based on the fact that matter consists of the particles, okay, which we today know as atoms and molecules, okay. Although Einstein was not very sure about his work, okay. So this was the importance of the Einstein relation. All right. Yeah, go ahead.
Sir, in the previous slide, like in the what you draw on the screen in iPad, like there you use 4DT. So like we'll be considering the case when that particle is moving in a plane, like only, right? Like,
Yes. Yeah, because when you're doing it, you have to look at the surface motion.
okay, so like kind of a thin film over which it is.
Yeah.
Okay, okay.
Because I have seen a video. I have shown you a video of Brownian motion. So polymer molecules typically just do a zigzag motion on the surface, right? You should be. You should be able to see them. Tracking the 3D motion is really very difficult. I mean, even today. All right.
Yes.
I mean, with a simple microscope. Now there are very complex techniques to see all kinds of motions in 3D inside the cells. But in older days, I mean, you could see the 2D motion with a simple microscope. All right. Now what I'm going to do? I'm going to play the trailer of a movie, and you tell me which movie is this. Okay.
This war, we're not winning it. If you speak a word of what I'm about to show you, you will be executed.
Anyone? Which movie is this?
Imitation game.
Very nice. Okay. So this is a lecture on diffusion and Brownian motion, and I'm showing you a trailer of imitation games. Is there any connection? Do you think that there is any connection, or this is something which is completely random I brought to the lecture? All right, so let me first play this entire movie trailer, and then I will talk.
For high treason. Who are you?
Alan Turing, one of the best mathematicians in the world.
Welcome to Enigma.
It's the greatest encryption device in history. The Germans use it for all major communications. 159 million possible settings.
It's unbreakable.
Let me try, and we'll know for sure.
So Turing, do you know how many have died because of Enigma? 3. While we've been having this conversation.
Churchill's put Alan in charge.
Keith and Charles both fired.
Popular at school, eh?
All right. I will stop it here. So now can you recall any connection with diffusion and Brownian motion? So here one of the major character was of Alan Turing in this movie Imitation Games? Is there any connection of Alan Turing to Brownian motion and diffusion? All right, so let me give you the answer. So Alan Turing, whom you know through the movie Imitation Games, he's supposed to be one of the great mathematician. He's also supposed to be a early computer scientist. But many of you don't know that Alan Turing was also a pioneer in a field which is called reaction diffusion system. Okay, so we have seen that diffusion is a very interesting phenomenon. Okay, but if diffusion gets combined with a chemical reaction, it becomes a even much more richer system. Okay, and Alan Turing was also a pioneer in the field of reaction diffusion system. Okay, now you know that many of the wild animals, fishes have very interesting, even snakes have very interesting pattern on their skin. And in older days, people were trying to understand how these animals gave these kind of exotic patterns on their skin, because many of these animals just get killed for their skin. And scientists were also trying to understand the pattern formation in nature. And one of the ideas that existed in those days was that there are morphogens, or chemical molecules that give rise to the color to the animal skin. So these morphogens diffuse on the animal skin, they react with one another, and that's how they form different types of interesting pattern on the animal skin. So reaction diffusion system was something which was used by the scientists in early days to understand pattern formation in nature. Okay, so Alan Turing in fact wrote an article. The title of this article is The Chemical Basis of Morphogenesis. Okay, and if you are interested into this subject of reaction diffusion system, which is even much more richer system than diffusion equation, you should definitely read this article. The title of the article, which is published in Science, is Reaction Diffusion Model as a Framework for Understanding Biological Pattern Formation. What is shown here in what is described in this article, let's say, suppose you have two different types of morphogens, and let's say if these two different types of morphogens can simply diffuse inside a container, then by having different types of boundary condition, you can generate different types of patterns. So all the patterns that you see here, okay, all of these patterns have been generated by solving the same reaction diffusion equation, but with slightly different conditions. And all of these patterns are called Turing pattern because based on the name of Alan Turing. What you see here is that this is a natural pattern on a shell. The same pattern has been generated on the computer by solving the reaction diffusion equation. Okay, natural pattern, artificially generated pattern, natural pattern, artificially generated pattern, natural pattern on a fish skin, artificially generated pattern, natural pattern, and artificially generated pattern by solving the reaction diffusion equation. Okay, so the whole point of you telling about the reaction diffusion system and Alan Turing is that Alan Turing, whom we know as one of the brightest mathematician, computer scientist, he also tried to do the biology to understand the pattern formation in nature. He was a pioneer in the field of the reaction diffusion system. And now it is very well established that animals don't get the pattern on their skin by using this simple mechanism of reaction and diffusion system. So Alan Turing was also interested in this field of reaction diffusion system. All right. So this is the summary of today's lecture. Today I talked about the Fick's law and continuity equation, and by combining both of them, we got the diffusion equation, which describes the process of diffusion. It connects the change of concentration with respect to space to the change of concentration with respect to time. And then we looked at the solution of the diffusion equation in a very simple case, which was diffusion from a point source. So diffusion equation looks like very simple, but it's one of the very hardest equation to solve. Then what I told you that diffusion is a very slow process because x grows as t to the power of half. X is not proportional to t like ballistic motion, and our cells cannot use the simple mechanism of diffusion to transport things from one place to the other place because it's a very slow process, and our cells use motor proteins to transport the things from one place to the other place directionally. After that, I talked about the contribution of Einstein to the field of Brownian motion. I derived the Einstein relation. I told you what was its significance in year 1995. One could calculate the Avogadro's number using the Einstein relation, and his derivation of the Einstein relation gave a very strong support to molecular kinetic theory of heat. And finally, I told you about the reaction diffusion system. And I also told you that Alan Turing, whom we know as one of the great mathematician and computer scientist, was also a pioneer in the field of reaction diffusion system, which is a much more research system than a simple system where diffusion is happening. All right. So with this, I will stop here and I will take the questions that you may. So let me stop the recording.